All right, let's dive into a really huge idea in computer science today, Hoare logic. We're going to explore how it's even possible to go beyond just testing code and to actually mathematically prove that a program is rock-solid reliable. You know the feeling, right? Some frustrating bug, a system that crashes at the worst possible moment, or an app that just doesn't work. It really makes you wonder, in a world that completely runs on code, how can we get past just hoping for the best and actually be certain a program is correct? Well, this phrase right here, this is the core promise of the approach we're about to unpack. It's a way of thinking that gives us a super rigorous method for guaranteeing software works, one logical step at a time.
So here's our game plan. We'll start with the hunt for truly correct code, then we'll see how a mathematical revolution changed everything. We'll get right into the heart of it with Hoare's triples, see how that logic grew and evolved, and finally, we'll talk about its absolutely monumental legacy.
Okay, so our story begins with a pretty fundamental problem. Back in the early days, software was simpler. But as it got more and more complex, making sure it was reliable became incredibly difficult. With critical systems on the line, the stakes were just getting higher and higher, and we desperately needed a better way.
And here's the thing. The real breakthrough wasn't going to be about just writing better code. It was about thinking about code in a totally different way. The challenge wasn't just make it work. The challenge became, can you prove with mathematical certainty that it will always work the way you expect? And that required a whole new formal approach.
And this is where computer scientist C.A.R. Hoare enters the picture. He came along and introduced a totally radical new philosophy that completely reframed how people thought about programming. Just let that sink in. This statement from Hoare is so powerful. He was arguing that programming shouldn't be seen as just a craft, like building a cabinet. It should be treated as a branch of mathematics. Because if a program is just a mathematical expression, well, then we can use all the tools of logic and proof to analyze it. This was an absolute game changer.
So you're probably asking, okay, great idea, but how do you actually do that? Well, the answer is this elegant and incredibly powerful invention at the very heart of his logic, the Hoare triple.
This is the fundamental building block of the whole thing. A Hoare triple is just a formal statement made up of 3 parts. It's always written in this very specific way. Something in curly braces, then the chunk of code, and then another statement in curly braces. Let's break this down. It's actually super simple. Imagine our program is just one little line of code, x equals x plus 1. So first, you have the precondition. This is what has to be true before you even run the code. Let's say, for example, our precondition is x equals 5. Then, second, you have the program itself, which is just x equals x plus 1. And third, you have the postcondition. This is what's guaranteed to be true after the code is done. So in our little example, the postcondition would have to be x equals 6. See? It's that precise. Honestly, the best way to think about it is as a contract for your code. It makes a very specific promise. If you fulfill your side of the bargain, the precondition, then the program guarantees it will deliver the postcondition. So if x equals 5 before we run the code, the program guarantees that x will equal 6 after. It's a logical if-then statement for how software behaves.
But of course, this foundational idea was just the beginning. The world of software kept getting more complicated, so Hoare's logic had to evolve to keep up with these new, more complex challenges.
Just think about it. Modern software isn't just about simple inputs and outputs anymore. We care about performance, about how fast things run. We care about how programs can handle doing multiple things at once. That's called concurrency. The original logic was powerful, but it needed some upgrades.
And so, people started building on top of that foundation. The logic was extended to analyze performance and figure out time costs. For concurrency, programs doing multiple things at the same time, new systems were developed, like one called Communicating Sequential Processes, or CSP, which helps prove they behave correctly. The logic also grew to verify things called monitors, which make sure all those parallel processes don't step on each other's toes. It was even adapted to get better at tracing errors.
So you can see this was way more than just a clever trick. Hoare's contribution fundamentally rewired computer science, and it is really hard to overstate just how important it was. This comparison, well, it says it all. Think about it. Just like Euclid laid down the fundamental rules, the axioms for all of geometry, Hoare did the same thing for computation. He gave us the logical bedrock, the absolute foundation that we can use to build proofs about software. And don't think for a second this is just some old academic theory. Hoare's legacy is alive and kicking in major modern efforts like the Verified Software Initiative. This group applies these exact same rigorous mathematical methods to build today's super reliable industrial-scale software, building proof right into the development process.
Okay, so to sum it all up, Hoare logic gives us a real mathematical way to prove our code does what we say it does. Its power comes from that simple idea, the Hoare triple, which is basically a logical contract. This whole approach turned programming from a craft into a formal, rigorous discipline, and its influence is absolutely foundational for the trustworthy software we all rely on today.
And that kind of brings us to one last thought. Now that we know it's possible to prove software is correct with this level of certainty, what should our standards be? What should we really demand from the critical software that runs our finances, our transportation, our whole lives? It's a pretty powerful question to think about.